In the Threads and Spinons theory, iron's unique magnetic properties arise due to its atomic structure and the behavior of its threads and spinners. However, the problem of why iron requires external forces, like a magnetic field, to become magnetized rather than being permanently magnetized, is rooted in several key features of its molecular and thread dynamics. Why iron exhibits magnetic behavior. 1. Abundance of free threads. Iron atoms have unpaired electrons in their outer shell. These unpaired electrons create threads that can interact strongly with external fields. The threads are not inherently aligned, allowing their orientation flexibility. This abundance of free threads makes iron highly susceptible to alignment under external magnetic influences. 2. Weak initial alignment. In its natural state, iron's threads and spinners are randomly oriented across its molecular domains. This random orientation cancels out any net magnetic field, leaving the iron unmagnetized. Even though the threads have potential for alignment, they lack a self-sustaining mechanism to maintain a permanent orientation without external help. 3. Atomic spin interactions. Because of its threads and spinners, each iron atom acts as a small magnetic dipole. However, the interactions between neighboring atoms' threads and spinners are not strong enough to force global alignment without an external force. Why magnetization requires external forces? 1. Thermal energy disruption. At room temperature, thermal energy causes random vibrations in the threads and spinners of iron atoms, disrupting any spontaneous alignment. These thermal disruptions overpower the weak thread-thread coupling between neighboring atoms, preventing long-range alignment. 2. Domain structure. Iron comprises magnetic domains, regions where threads and spinners are aligned locally. However, in an unmagnetized state, these domains are oriented randomly relative to each other. External forces, such as a magnetic field, must align these domains and their threads, producing a net magnetic field. 3. Energy barriers. Aligning the threads and spinners of iron atoms across its structure requires overcoming energy barriers created by the interactions between threads. External magnetic fields provide the energy necessary to overcome these barriers. How iron retains magnetism. Once iron is magnetized, aligned threads, the threads and spinners of the domains become aligned, creating a self-reinforcing tension that maintains the alignment. 2. Stable domains. In a strongly magnetized state, the thread-thread coupling between neighboring domains becomes strong enough to resist thermal disruption, allowing the material to retain its magnetic field. 3. Thread locking. In some cases, external forces can lock threads into alignment by inducing changes in the material's atomic structure, making the alignment semi-permanent, as in a permanent magnet. Defining the magnetic field of iron. Key concept. In the Threads and Spinons theory, the magnetic field of iron arises due to the alignment of its molecules, which involves threads and spinners interacting in a coordinated fashion. Iron's molecular structure. Iron atoms, when magnetized, align their threads, electron paths, in the same direction. This alignment occurs when external magnetic fields or forces cause the threads and spinners of adjacent iron atoms to synchronize. Threads in action. Each atom has threads, continuous lines of tension that extend outward. When threads align, they generate a cumulative tension, creating a magnetic field. Formation of the magnetic field. 1. Unaligned state. In an unmagnetized piece of iron, the threads and spinners within molecules are randomly oriented, canceling out the net magnetic field. 2. Aligned state. When subjected to a magnetic field, the threads and spinners of iron molecules align. This alignment causes the cumulative tension in threads to produce a magnetic field. The spinners, rotational components of threads, orient themselves synchronized, generating a unified directional force. This alignment results in a field propagating outward as tension waves along the threads. Attraction and repulsion. Attraction. When the threads of two objects are aligned in the same direction, their spinners rotate in synchronization. The thread tension creates a pull between the objects, manifesting as a magnetic attraction. Repulsion. When the threads of two objects are aligned in opposite directions, the spinners' rotations conflict. This creates a push as the tension fields repel each other. Magnetic field strength formula. The magnetic field strength B in the Threads and Spinons theory is expressed as example calculation, explanation of units, key insights. Alignment. determines strength. The more significant the proportion of aligned threads, the stronger the magnetic field. Attraction and repulsion depend on thread alignment. Magnetic poles attract or repel based on whether their threads and spinners are synchronized or opposed. Thread tension drives magnetic properties. The tension in threads not only determines the field strength, but also explains the spatial propagation of magnetic forces.